Well, good afternoon. First of all, I'd like to thank the director for his kind comments and Manda Murali for inviting me here to give this public lecture. What I'd like to do is tell you something about electronic devices that utilize the spin of the electron to enable new functionalities. And this is a relatively new field of research. It's about 25 years old, and it evolves from our ability to create new materials on the atomic scale by combining magnetic and non-magnetic layers in non-equilibrium structures. And I want to show you how we could do that and then utilize the spin of the electron to create devices that are extremely sensitive detectors of magnetic field and that have already allowed us to increase the storage capacity of magnetic disk drives by 1,000-fold. But I'd also want to comment on the future devices that could be enabled by Spintronics, including novel, non-volatile memories, and in particular a racetrack memory, which could, in my mind, replace magnetic disk drives in the future. If there's time, also, I might discuss some cognitive devices that are based on Spintronics and other phenomena. So in context, today, the information technology businesses are undergoing an enormous revolution, and this has been enabled in some sense by Spintronics. This is the revolution of big data. Our ability to access all data that ever has been created enables entirely new businesses and opportunities for new industries. And that's happening at an accelerating pace. And essentially what is required for these industries is the ability to access digital data extremely cheaply and efficiently. And that is what Spintronics has enabled. So I'd like to tell you a little bit about the history of Spintronics leading up to the devices that, in my mind, are going to be the most important devices for storing digital data in the future. Just as a comment, I'm an IBM fellow in IBM Research, and I've actually been carrying out research here in California, in San Jose, for the last almost 30 years. And I just want to show you a picture. It's a beautiful location. IBM has 12 corporate research labs around the world. And in the bottom corner, you can see a thin film deposition system that we spent about 10 years building, which really enables us to engineer structures on the atomic scale using a wide variety of thin film deposition techniques. I'm actually not going to say any more about this capability. And last year, I took up a new position as director, one of the directors of the Max Planck Institute for Microstructure Physics, which has a significant history in spin-polarized electron physics through the work of Jürgen Kirschner. And I just wanted to show you this because I'm going to maintain my position at IBM as well as being director here at this institute and also a professor at the Martin Luther University. So I wanted to encourage any of you who might want to do a PhD or a postdoc or consider being a junior group leader to consider writing to me. We have a lot of available positions. So back to big data, and this chart shows you how the total storage capacity of all the data in the world has evolved over the past 2 decades. I'm not going to discuss this in any detail. What this chart shows is that there has been, as you all know, an exponential increase in our capacity to store data on all the world's devices. But most importantly, there's been an enormous revolution just in the past decade. Until a decade ago, most data was stored in an analog form. These are the technologies shown here as orange. So the pie charts shows you the distribution of devices and their technological basis for storing data. And until just a few years ago, most data was stored in an analog form in terms of paper and books and films and videotape. But in the past 10 years, then nearly all data today is rather stored in a digital format, and nearly all of that in magnetic disk drives using spintronic devices to read the information. This is what has enabled the enormous transformation of many technologies that we know today in the IT industries. But if we look back 50 years, then magnetism has played a significant role in our ability to store data for, as I said, more than half a century. This is one of the very earliest devices that was devised to store digital data. Some of you may have heard of this. It's a magnetic core memory. And what you can see in this foil is you can see here a series of magnetic rings or magnetic disks, which are made of very soft magnetic material. These are millimeters in size, and to read and write data into these disks, copper wires, shown as these red and green wires, were passed through the middle of these disks. So it's a technology that did not scale well. And in fact, this technology was used only for a few years. IBM built some of these early magnetic core memory devices. And indeed, this is a photograph I took of one of these devices. It has about 3,000 bit storage, 3 kilobit storage capacity. And this was dating from about 50 years ago. And shown here in the cartoon is how it works. Here is a soft magnetic ring, and the information is stored as the direction of magnetization around this ring, whether clockwise or whether anti-clockwise. And so there are two very important ingredients here in the physics. One is this, if you like, chiral nature. The chirality here, clockwise and anti-clockwise, determines the state of this memory. And secondly, this memory has a very important feature that the magnetic flux that is otherwise given rise to by magnetic materials is entirely enclosed within these disks. And it turns out that's extremely important in building magnetic memories, and I'm going to come back to that a little bit later. So what does spintronics mean? Spintronics is the concept that we can create entirely new materials and devices whose properties are determined by flowing currents, not of pure current, but of electrons which are spin polarized. And shown in green is already the impact of these materials. This has been in our ability to create, at room temperature, the world's most sensitive detectors of small magnetic field. First by something called a spin valve, and more recently by something called a magnetic tunnel junction. And I'm going to briefly discuss what they are. Then in the future, we can imagine some entirely different devices to store information, a magnetic random access memory and a magnetic racetrack. And we can even use these spintronic devices to build synaptic connections that might enable us to build computers that think more like the brain. This is something I'm not going to talk about. And also something I'm not going to discuss is the possibility of creating entirely new forms of logic that potentially could use extremely low energy. And there have been a number of postulates that we could build new logic devices using tiny nanomagnets that interact with each other, their fringing fields. But actually, I don't think that is so interesting. More interesting is the concept of building ultra-fast switches, not from ferromagnetic, but from anti-ferromagnetic materials that are insulators. And on the very short timescale, on the picosecond timescale, by applying very short optical pulses, terahertz pulses of light, we can turn these anti-ferromagnetic insulators into metals for a few hundred picoseconds. So this enables us to build extremely fast switches or latches. Again, that's not something I'm going to discuss in this talk. So if we go back to basics, then of course you're all familiar with the concept that an electron and the charge of the electron enables us to build memory and storage devices. Memory devices by storing a certain number of electrons with a certain charge in a capacitive device, and logic by controlling the flow of currents of electrons, and their magnitude determines the on and off state of, for example, transistors. But the electron has, as you all know, a very important property, its spin, and essentially all one needs to know about this electron spin is that it's a quantum mechanical property which only takes two values. The electron spin is either essentially up or it's down. And by understanding this and manipulating the spin, we can create interesting devices for the purposes of sensing and memory applications. So this is the concept. Here, if we take, for example, a wire which is made from a non-magnetic metal like copper, you're all familiar with, and if we have a battery and we introduce current, the current consists of 50% electrons with spin up and 50% with spin down. And nothing much happens in this non-magnetic metal. The current will be carried equally by electrons which are spin up and spin down. However, a very interesting effect happens if we introduce from the same battery where we have 50% upspin electrons and 50% downspin electrons. If we now introduce that current into a magnetic material where this blue color represents magnetization pointing to your right, then with a short distance of introducing this unspin polarized current, it becomes spin polarized because the upspin and downspin electrons are scattered at different rates in a magnetic metal. So this magnetic metal, as shown here, you can see that the current is carried here 75% by these blue electrons and 25% by the other spin polarized electrons. So because spin-dependent scattering, the current in nearly all magnetic metals is spin-polarized and is carried largely by one spin orientation. This was a phenomenon that was first proposed by Neville Mott in the 1930s. So this concept of spin-polarized current in a ferromagnet underlies a discovery that was made in 1988 and 1986 by Albert Fert and Peter Grunberg called giant magnetoresistance. So some of you may have heard of this. They were awarded the Nobel Prize in 2007 for their discovery of this phenomenon. And what they found was that if you take a magnetic multilayer shown in this cartoon, you have blue and red layers, which are magnetic layers of iron, separated by a thin layer of chromium. And Peter Grunberg discovered that two layers of iron separated by 9 angstroms of chromium, their moments are always oriented anti-parallel or anti-ferromagnetically to one another in zero magnetic field. And then what Peter and Albert discovered was that when you applied a large enough magnetic field, you could change the orientation of these magnetic layers so they become parallel to the magnetic field in either the positive or negative field direction. And they found at low temperatures that this resistance of this multi-layered structure would decrease by about a factor of 2. But the magnetic fields required a very large, this is 20,000 Ørsteds, about 20,000 times the Earth's magnetic field. And also they grew these materials to be epitaxial, single crystal films made by molecular beam epitaxy. They also found that they saw this phenomenon only for one thickness of chromium. When you increased the chromium thickness, the phenomenon decayed, but monotonically. So this was an interesting discovery of physics, but it wasn't clear that this could be useful from a technology point of view. So what I showed was that this phenomenon wasn't restricted to iron and chromium is a very special metal that by itself is anti-ferromagnetic, and that was thought to play a role in the phenomenon of giant magnetoresistance. I showed, in fact, it's a phenomenon that is, can be seen in nearly all magnetic systems where you have magnetic layers separated by thin non-magnetic layers. And I discovered that the largest effects are found at room temperature in this system here, comprised of ultra-thin cobalt layers separated by ultra-thin copper layers. These layers are about 3 atomic layers thick, each of them. And then again, through the copper, the magnetic layers become strongly aligned anti-parallel to one another in zero field. And again, if you apply large enough fields, here about 30,000 Ørsteds, the resistance drops. And this is certainly an interesting and general phenomenon. So it turns out that in the early days of GMR, the phenomenon was poorly understood, and the effect was believed to be related to this whole concept of spin-dependent scattering within the bulk of the magnetic layers. But it turns out that, as I showed, this effect really is derived from scattering at the interfaces between the magnetic and non-magnetic layers. It turns out this is extremely important in order to understand the physics, but it turns out to be very important technologically, because this means one could use very thin magnetic layers to achieve large changes in resistance. And this is very, very important to create sensitive field sensing devices that can detect tiny magnetic bits. It turns out in a few years' time, I looked at about 100,000 different thin film structures because the effect was so poorly understood. But as part of this, I showed even using simple techniques, sputter-deposition is a very simple technique for depositing thin films. I could show that we could change these structures by subatomic layer thicknesses and see dramatic changes in the magnitude of this giant magnetoresistance effect. So let's get back to how this could work technologically. We need to reduce the magnetic field by about 10,000 times to make these phenomena useful technologically. And we can do this using this structure. It's a sandwich of 2 magnetic layers. Here you see the blue and the red, again, represent the different orientations of these magnetic layers. And they're separated by a non-magnetic layer of copper. So in this geometry, what happens when we introduce unpolarized current from this battery into this sandwich? Then these blue electrons are weakly scattered in this blue layer, but are strongly scattered in the upper layer with its magnetization in the opposite direction. On the other hand, these red upside polarized electrons are weakly scattered in the top layer, but are strongly scattered in the lower layer. So when these layers are thin enough that the electrons from one layer can sense the other magnetic layer, in other words, this copper layer thickness is below the mean free path in copper, which is significant at room temperature, then all the electrons, whether they're spin polarized up or down, are strongly scattered somewhere in this sandwich. However, if we now change the orientation of one of these magnetic layers, so the two magnetic layers are now aligned in the same direction, now it turns out when we introduce current from a battery, then the blue electrons are weakly scattered everywhere in this structure. Effectively, they can provide a short circuit through this sandwich. So this sandwich has a lower resistance than the upper sandwich because one polarization of the electrons can travel through this structure with little scattering. So for these reasons, we call this a spin valve device, effectively a device where we can turn on and off the current by changing the magnetic orientation of these two layers. So this then enables us to build a sensitive detection device. And so this, for example, is the property of one of these spin valve structures. And we have to use some other tricks, which I'm not going to discuss. I call it spin engineering, where we engineer the magnetic structure so that the magnetic moment of one of these layers is always fixed in one direction for all useful fields that we might apply. And only the second magnetic layer, separated by this thin layer of copper, will respond to an external magnetic field. So in this way, you can see in this resistance versus field loop that now the resistance is changing not on a 10,000 Ørsted scale, but on a 1 Ørsted scale. And this is because we've basically got no coupling through the copper, but we can engineer the structure so one magnetic moment will respond to very tiny magnetic fields. Now it turns out then that the change in resistance, and you see this stepwise change in resistance as one of the layers goes from being parallel to the fixed layer to being antiparallel, this stepwise change in resistance at room temperature is of the order of 10 or 20% rather than 100% in the multilayers. So we've reduced the change in resistance by a factor of 10, but we've reduced the field required to see that change by more than 10,000 times. So we've created a much more sensitive detector of small magnetic fields. And this spin valve sensor then is today one of the most sensitive detectors of small magnetic fields that is known at room temperature. Now, a very interesting phenomenon that I also discovered was that unlike the original work of Fett and Grunberg, in which they found that the magnetoresistance was insensitive to the thickness of the spacer layer in iron chromium superlattices, I found that in these cobalt copper and also in iron chromium, you see that as you vary the copper layer thickness, the magnitude of this giant magnetoresistance changes from large values to 0 values, and it oscillates as a function of increasing spacer layer thickness. And the reason for this is a long-range oscillatory interlayer coupling between these magnetic layers. So for each copper thickness where we see a giant magnetoresistance effect, that's a thickness where in zero field the magnetic layers are coupled antiparallel to one another. But for intermediate thicknesses, the layers are coupled parallel to one another. So the copper itself becomes magnetic, and the magnetism is of a long-range oscillatory spin density wave that leads to coupling of the magnetic layers, which is either anti-ferromagnetic or ferromagnetic, and it oscillates with a period of copper which is just a few angstroms and which depends upon the crystal orientation. So here you can see some single crystal structures we made by sputtering, a very simple technique, different substrates, and depending upon whether they're oriented in the 100, 110, or 111 crystal orientations, we see different copper thicknesses at which the giant magnetoresistance reflecting the anti-ferromagnetic coupling through the copper is established. And we can use this phenomenon then to engineer magnetic structures with particular magnetic configurations. And the basic physics is extremely simple. If you introduce into an electron C, for example, an impurity in a non-magnetic metal, then you all know that that impurity, that charge impurity, will be screened by the conduction electrons. But because the wave vectors of these electrons is cut off at the Fermi energy, that leads to a density wave, a charge density wave. This is a Friedel charge density wave. But in the case of a magnetic material, the polarization of the electron gas is no longer charge-based, it's spin-based. And you have an oscillation in the density of spin-polarized electrons with a period that reflects the Fermi surface topology. And in the case of magnetic multilayers or a sandwich structure with two magnetic layers, then now you have essentially a density wave that extends from these magnetic interfaces. And depending upon the number of periods of this spin density wave, the magnetic layers are coupled anti-ferromagnetically or ferromagnetically. And as we change the thickness from a full to half period of these oscillations, then the coupling changes from a ferromagnetic to an anti-ferromagnetic coupling. Well, it turns out this period, this oscillatory long-range exchange coupling hadn't been seen before my work, and by looking at a lot of different thin structures, we could show that it's essentially a universal property of all the elements in the periodic table. So all of these 3D, 4D, and 5D non-magnetic elements give rise to this long-range oscillatory exchange coupling, whose strength varies as we increase the D-band filling and varies as we go from the 5D to the 4D to the 3D metals. It systematically increases. And so this enabled us to understand the origin. It's due to the potential mismatch between the electronic bands in the non-magnetic metal and the magnetic metal. So why is this important? It turns out, as I mentioned in the very first case for magnetic core memory, then magnetic materials give rise to long-range dipolar coupling fields, which means that magnetic materials interact. So on the nanoscale, this becomes increasingly important. So for example, if we make a spin valve structure like this with two magnetic layers separated by copper, where we fix the magnetization of one of these layers, then on the nanoscale, as we reduce the dimensions below a micron or below 100 nanometers, then the fringing fields from the magnetic poles at either side of this magnetic structure gives rise to a very large interaction, a dipolar interaction between these two magnetic layers that increases inversely with the size of this device. So on the nanoscale, these fringing fields can be of the order of hundreds of oersteds, very, very large. And in order to make a useful device, we have to overcome this extremely large dipolar field. So I proposed building something I called an artificial antiferromagnetic structure. And essentially, this magnetic layer, we can eliminate the magnetization and the long-range dipolar fields by forming it from a sandwich of two magnetic layers coupled anti-parallel to one another through an atomically thin layer of ruthenium, which gives rise to the largest coupling of any of those non-magnetic elements, the largest anti-ferromagnetic coupling. And so now essentially this reference layer has no net magnetization. But because this phenomenon of giant magnetoresistance relates to interface scattering, then the interface which remains magnetic can give rise to spin-dependent scattering and gives rise to a magnetoresistance in the structure, but this layer itself has no net magnetization, and so no longer interacts with this layer, this sensing layer, which will detect the small magnetic fields. So this is a very, very important aspect of building any type of magnetic structure on the nanoscale. We have to control these long-range dipolar fields, which become increasingly important as the scale of the device is diminished. So now, why was this important? This spin-engineered spin valve structure we could then use to detect magnetic fields. And some of you may be familiar with a magnetic disk drive. Basically, you have a glass disk which is rotating at high speed below a device that is used to both write and read information which is stored in a magnetic film, the magnetic media, which is deposited on this glass surface. So the information is really encoded not in the magnetic regions themselves, but as the boundaries or the domain walls or the transitions between magnetic regions with magnetization pointing here to the right or to the left. And we detect these fringing fields by their change in the resistance of this spin valve engineered structure, which we can deposit on the back side of a small ceramic object, the recording head, which today is riding above this glass disc, only at a separation of only 1 nanometer, during the reading and writing process. So it's an amazing technology that works even though it's mechanical and involves a large object, the disk in which we store this information. So as the disk rotates underneath this recording head, the spin valve sensor will see these transitions, and we detect them by the resistance change in this sensor. So if we now look at the evolution of magnetic disk drives over the last 50 years, then IBM, it turns out, invented the magnetic disk drive in the 1950s. And during the 50 years that IBM owned a disk drive business, it sold this business in 2002, then you can see the areal density, or the number of bits per unit area, here in gigabits per square inch, evolved by 9 orders of magnitude. But several of those orders of magnitude were due to our introduction of this spin valve device in 1997. And since then, we could improve the storage capacity by several orders of magnitude because of the extreme sensitivity of this device to detecting tiny magnetic fields. Therefore, we could make these magnetic regions much smaller, 1,000 times, or today even 10,000 times smaller in area. And then we can see this in real devices. This is a magnetic disk drive that is in one of IBM's buildings in California, in San Jose. It was built in 1962, and this device has 50 disks. Each disk is 24 inches in diameter, and the total capacity of this device is 28 megabytes. And we can compare that then to today's device. This is one of my own disk drives from 2012. It has about 1 terabyte of storage in one disk, only 2.5 inches in diameter. And a lot of this improvement is due to Spintronics and our ability to detect tiny magnetic regions so sensitively. So this then is the introduction. Spintronics led to the spin valve sensor, and this has enabled us to increase the storage capacity of magnetic disk drives so much so that all information known to mankind can now be stored and accessed in magnetic disk drives. This is what makes possible access to essentially all information, and it's in a digital form, which means it's searchable, and one can carry out data analytics on this data. So what is the future? Spintronics then has the ability to potentially replace not only improve magnetic disk drives, but could replace a magnetic disk drive with a completely solid-state device, which I've called Racetrack Memory, and I'd like to briefly discuss that. But before that, I want to discuss briefly something called a magnetic random access memory, which is based on something called a magnetic tunnel junction. So a tunnel junction device is essentially the same as a spin valve device. It looks identical. The spin-engineered structure is identical, except the copper layer that separated these two magnetic layers is replaced with an insulating or dielectric material, which does not conduct electricity. So now instead of flowing current parallel to these layers, the current is flown perpendicular, and the physics has got nothing to do with giant magnetoresistance, spin-dependent scattering. It's a different physics. It's spin-dependent tunneling of the electrons. And the electrons, again, can tunnel easily when the magnetic layers are parallel to one another, because again, the current is spin polarized, where now the polarization of the current reflects the electronic structure of the magnetic layer. And when we switch the moment of one of the magnetic layers so the two moments are antiparallel, we can essentially turn off this tunneling current. And what this device enables us to do, though, is to change and modify the resistance of the device by many orders of magnitude by simply changing the thickness of this dielectric layer, because the quantum mechanical tunneling process is exponentially decreasing with increasing thickness of this layer. At the same time, the magnetoresistance, the difference in resistance of these two states, remains the same. So this is a very, very interesting technology for a variety of reasons. And again, in order to build a useful device, we have to engineer the structure to control the magnetic moment directions as a function of magnetic field. But in this case, we designed the structure so that in zero field, there are two magnetic states. A magnetic state with a low resistance where the magnetic layers are parallel, and a magnetic state where the moments are antiparallel with higher resistance because the tunneling current is suppressed. And using conventional materials, aluminum oxide tunnel barriers are shown in this cross-section transmission electron micrograph. This is the magnetic material, and you can see no structure, no atoms in this aluminum oxide layer. Aluminum oxide is an amorphous material which can be made very thin so that all the electrons tunnel without any resistive or diffuse scattering of these electrons, which is very important to eliminate that diffuse scattering. But it turns out in an amorphous material, the electrons have wave functions of different symmetries. And because the structure of this insulating barrier is amorphous, the electronic structure, the wave function symmetry, is not important. But what was predicted by several theorists in the early 2000s was that if you had a structure which was crystalline of a particular orientation, and the tunnel barrier was also crystalline, now the wave function symmetry is important in determining the probability of tunneling of the electrons. And so we showed this was true for the first time using this structure, which consists of a cobalt ion, which is a body-centered cubic material, separated by a simple cubic magnesium oxide layer, which we could grow by sputtering again coherently. So the interface now is coherent, and it turns out in this case, the electrons, which are majority spin polarized, can tunnel much more readily because their wave functions are very S-like, very extended, and the tunneling matrix element, the probability of tunneling, is much larger than for the minority spin polarized electrons, whose wave functions are much more localized and extend only a small distance into the tunnel barrier. So effectively, this crystalline tunnel barrier will spin filter the electrons, only allowing electrons of one spin orientation to cross the tunnel barrier. And what does this mean? This means that we can see much larger changes in resistance of the structure. So the tunneling magnetoresistance, the percentage change in resistance from going to a parallel to an anti-parallel structure, is several 100% as compared with these metallic structures which are based on spin-dependent diffusive scattering, where the magnetoresistance is only about 10 or 20% at room temperature. And you can see this in the last 15 years, the magnitude of this tunneling magnetoresistance has enormously increased as we've been able to understand the physics and make structures with extremely exquisitely controlled tunnel barriers. And so just as, let me just show you one device. We've made some of these tunnel junction devices. The current has to flow perpendicular, so we need to use lithography to create devices, and we can build devices in my own laboratory down to a scale of, this is about 27 nanometers. Here you can see the tunnel barrier, and the electrons then cross from one magnetic electrode to the other. And in order to make useful devices for memory applications, we need to build devices on the scale of perhaps even 10 nanometers, much smaller. And it turns out on this scale, there's some problems with known materials in that the amount of magnetic material in one of these electrodes becomes so tiny that thermal fluctuations will cause its magnetization to switch from one direction to another. So an intense effort is underway to find new magnetic materials which will be able to sustain these thermal fluctuations without flipping their magnetic orientation. Now at the same time, I'm going to discuss next, we could switch these devices not by applying external magnetic fields, but by passing a large current through the device. Because it's spin polarized, we could use this current itself to switch the magnetization. And that limits, though, how many magnetic moments we can switch with a given current. So there's, again, a need for magnetic materials which are stable against thermal fluctuations, but yet can be switched with currents that can be delivered from minimum size transistors at the technology node in question. So how do we build then a memory device? And this is something we proposed a long time ago in 1995, and the concept is very simple. We create a cross-point array, which means here is a series of parallel word lines and a series of parallel bit lines, orthogonal to each other, and between each of these lines at each intersection point, we insert this tunnel junction device. And so to read this device, we pass a very small current along this line through the device and along the respective bit line. And depending upon the state of this magnetic tunnel junction, where the magnetic layers are antiparallel or parallel, that's the memory, how the memory information is stored, the resistance will be high or low. And we can detect this resistance state very quickly, in just a few nanoseconds. We did that in 1999. But in those days, we proposed switching the magnetic state of these devices by passing larger currents directly along the word lines and directly along the bit lines. And these currents create a self-magnetic field, the Ørsted field. And all the devices along this row see the same field. So we design this current and the associated field to be too small to switch these devices, but we apply a second current through the orthogonal bit line. And it's the combination of these two fields, one from the bit line current and one from the word line current, that at the intersection of these lines will cause this magnetic device to switch to one state or to the other state. And by reversing the direction of the current along the bit line, we can set that junction to the other state. This is what we proposed, and we actually built devices like this in 1999 that we showed worked, and we could switch these tunnel junction devices on just a few nanoseconds timescale. So it's a very, very interesting technology. But in order to make this work, again, we need materials that can have sufficient thermal stability, but yet can be switched not by magnetic fields, but by passing current through the. Let me get to that in a moment. So just to summarize, these tunnel junction devices then are already used in disk drives to read information because they have even greater sensitivity to detect tiny magnetic regions than the metallic spin valve structures, although the engineering, the spin engineering, is identical in these devices. Now, a disk drive provides enormous amounts of storage capacity, and it's very cheap. But at the same time, it's slow and unreliable because the disks themselves are massive and have to be rotated. So it takes about 10 milliseconds to access the first bit of information. And at the same time, because the recording head is floating above the surface of this disk at a very tiny distance, there's a possibility of catastrophic failure of this mechanical device. On the other hand, we could use this same tunnel junction as a memory device. The memory is the orientation of the magnetic layer in this device, whether parallel or antiparallel to the reference layer. And I've shown how we could visualize using magnetic fields to set the state of the device, but we could also use currents through these devices for changing their state. And this, for example, is a 16 megabit MRAM device that we built at IBM a few years ago. And we could demonstrate this as extremely high performance, nanosecond switching rather than millisecond access as in a disk drive, extremely good endurance, no failure mechanism as in disk drives, but at the same time, the cost of this memory is about 100 times higher per bit than in the disk drive. So it has very high cost. So you can see today in computing devices, we need to use this type of memory or something similar to this for the main memory of the computing device, where we need speed, but most of the data is stored in magnetic disk drives because it's 100 times cheaper to store data. So what I proposed about 10 years ago was we could potentially build a new device, which I called Racetrack Memory, which would be as cheap as a magnetic disk drive, but would have the same performance and reliability as conventional solid-state memory. And the concept is very, very different. The concept is shown here. We have a vertical wire of magnetic material above the surface of the silicon wafer. And this wire is magnetized in regions shown here as blue and red. And the information, again, is stored in the boundaries between these magnetic regions. But the new concept is that simply by passing a current into this wire, we can move all of this information around the wire at one point in the magnetic racetrack. This is the concept, and because, in principle, we could imagine storing 100 bits of information in this one racetrack, that would lead to a 100-fold decrease in the cost as compared to, for example, this magnetic random access memory. So the basic concept is we store information in this third dimension. And we simply bring that information down to one reading and one writing device per racetrack for the purposes of using this memory. And the physics that is on which this is based is a very interesting concept that was not realized only recently, but essentially the physics was originally proposed by Luc Berger in the 1980s and John Dzyaloshiinski somewhat later. And the idea is based on this early notion I mentioned, that if you bring an uncharged, unpolarized current from a battery into a magnetic material, it becomes spin polarized because of spin-dependent scattering. Now you have the electrons with their spins oriented in one direction, and that means each electron has an angular momentum, a spin angular momentum. So effectively you have a current of spin angular momentum, and by delivering that angular momentum to the magnetic lattice, we can cause magnetic moments to rotate, or, as in this case, the domain wall, which is the boundary between two magnetic regions, in this case magnetized in opposite directions, then every time we pass a conduction electron, which is polarized in one direction across this domain wall, it will adiabatically rotate its spin polarization and deliver a quantum of spin angular momentum to the magnetic atoms in the system. And for every electron that crosses this domain wall, we can rotate a single magnetic moment. So if we have a big enough current, we can cause all the moments to rotate, and the domain wall will be moved to the right, or if we reverse the current, to the left. And why is this important? Because we can move not just one domain wall, but a whole series of domain walls will all move in the same direction. And this is possible, for example, by applying magnetic fields. So until this concept was proven, the only method of manipulating magnetic moments was using magnetic fields. Here we can do it with current. Simply by passing current from a battery into a wire, we demonstrated all the domain walls will move. So we can propose, this is what I proposed, we have this sort of racetrack, a vertical racetrack. We could build a very interesting three-dimensional storage device that would have the capacity of a magnetic disk drive, but be 1,000,000 times faster and never break down. On the other hand, if we built more simply horizontal racetracks, we could build memory devices with the capacity of flash memory, which essentially today is one of the two largest memories used today. It's similar in manufacturing capacity as DRAM. And the concept again is here we have a device for writing the domains or the domain walls into the wires. Here we have a device for reading the domains as the domains are moved through the wire by applying a shift pulse of current. So this seems like a very interesting concept, and in the last several years we've demonstrated that it basically does work. It's possible to do this. So again, what we have to do is have a magnetic wire. We create magnetic regions by writing along the wire, and have a reading device which detects these domains as they're moved along the wire. This is the basic concept of racetrack memory. So we need essentially three transistors, one for moving the domains, one for reading, and one for writing. And we've built a prototype 3 years ago. We published the results in collaboration with ITRI, Technology Development Organization in Taiwan, and demonstrated proof of concept that this is possible. In this case, you can see 32 racetracks, or 32 wires, and each of these racetracks has a reading device, which is a magnetic tunnel junction. The writing device is a field from a current passed through a neighboring wire, and we built the circuits that were designed by our colleagues at ITRI in standard silicon that enabled us to demonstrate we could write, move, and read these information in these racetrack as shown here. However, at that time as you can see, the scale of this device is not useful technologically. It's useful of concept, but we need to reduce the dimensions here by probably a factor of 10 in order to make this a useful device. So I want to briefly discuss now some of the more recent work on racetrack and why we think this, or I think this is even more exciting. The demonstration I just showed you was using soft magnetic materials. And this means that the boundaries between magnetic regions, which here you can see the magnetization direction in a simulation shown as means the moments are pointing to your right, and green to the left, and blue is up, yellow is down. And in these soft magnetic materials, such as nickel iron, then you find that the domain walls are very large. They're either this vortex structure or this transverse wall structure where the magnetization rotates from the left to the right by pointing up or equally by pointing down. So these walls have a chirality, which is very important, it turns out, as does this vortex wall. The chirality here is anti-clockwise or clockwise, and in a uniform wire, they have the same energy. But it turns out the chirality of these domain walls will determine how they move in response to both field and current. For these soft magnetic materials, the domain walls tend to be very wide, about as wide of the wires themselves. Not useful technologically, but we can make much narrower wires by increasing the magnetic anisotropy, so the moments want to either be up or down, and that means the walls will shrink in proportion to the energy difference between the up and down directions. So we introduce some kind of magnetic anisotropy that forces the magnetic moments, in this case, to be pointing perpendicular to the plane of the wire. And we can do that by creating multi-layers of atomically thin magnetic layers. For example, we could use a few angstroms of cobalt separated by a few angstroms of nickel. And the interface breaks the symmetry and forces the magnetization to want to be perpendicular to the layers. This is perpendicular magnetic anisotropy. Now what we've discovered, and some other groups around the world in the last 2 years, is that we can move the domain walls in this structure much more easily than in these soft magnetic structures when we combine this multi-layered ferromagnetic structure with underlayers formed from heavy metals like platinum, palladium, and iridium. And I want to briefly discuss this effect, which is a little bit more technical. But the point is this: if we introduce a current into this wire, we can move domain walls. And the domain wall velocity is shown here as a function of current density. So I told you that we need a lot of current to switch enough magnetic moments to move a domain wall. And typically, we need a current of the order of 10 to the 8 amps per square centimeter, and the domain walls will move at about 50 meters per second in wires like this, where we have very many cobalt and nickel layers. So we have very many of these bilayer structures, the moments are perpendicular, and the domain walls move at about 50 meters per second for these current densities along the direction of electron, because the current is delivering spin angular momentum in that direction. So the domain walls move, as we suspect, in the direction of the flow of spin angular momentum created by spin-dependent scattering within the interior or the volume of these layers. That's what happens. And these are our results here, and this is some work by Teruo Ono in Kyoto. Now, what was a big surprise was 3 years ago, Mikhail Miron discovered that if he took a single layer of cobalt, just a few angstroms thick, deposited this on platinum and covered it with aluminum oxide, which is an insulator, he found now the domain walls moved much faster. You see 300 meters per second, and they moved not in the direction of spin angular momentum, but they moved in exactly the opposite direction, in the direction of current. And that's what we find too if we make this multi-layered structure formed from cobalt and nickel. We make it very, very thin. In this case, it's 1 nanometer thick, and deposit it on platinum. Now the domain walls no longer move in the direction of the spin angular momentum within the interior of the magnetic layers. They move exactly in the opposite direction, and they move several times faster. And you can see that the critical current density needed to move the domain walls is much smaller. So the question is why? And this has been a puzzle for the past 2 or 3 years, and we believe that we have unraveled the answer, and it's due to a rather complex interplay of 4 phenomena derived from spin-orbit coupling. First of all, the fact that these magnetic moments are perpendicular to the layers is a consequence of spin-orbit coupling and broken symmetry. And it turns out these heavy metal underlayers, platinum, iridium, palladium, they become slightly magnetic. So there's a very large proximity-induced magnetization in these layers, again derived from spin-orbit coupling. And this gives rise to a very interesting exchange interaction which causes the moments in these cobalt layers not to be parallel or antiparallel, but to be exactly perpendicular to each other in a chiral manner. And then finally, the current flowing through a heavy metal like platinum becomes spin polarized due to spin-dependent scattering in the platinum metal. And you end up with a spin current that is generated that flows from the platinum into these magnetic layers. This is very complicated, but we have unraveled all of this in the last couple of years. So using these perpendicularly magnetized ultra-thin layers on platinum, we can move domain walls much faster than in these soft magnetic metals. And here's a demonstration. You can see here 20 domain walls which are moving backwards and forwards as we apply nanosecond-long current pulses. And we're imaging this using curve microscopy in wires that are about 2 microns wide. But you can see all these walls are moving together in one direction and the other direction. And they're moving at high velocity at low current density. They're moving at a few hundred meters per second. And the domain walls here are very narrow. They're about 6 nanometers wide. And the racetracks themselves are only 1 nanometer thick, which means we can inject domain walls using a number of very interesting new techniques. We don't need to use magnetic fields. However, the final unsolved problem with this approach is the fringing magnetic fields that I come back to. So these magnetic moments that are perpendicular to these layers generate magnetic fields. So these domains interact with one another. And the domain walls will simply interact, and eventually, if we put them close enough, will cause the domain walls to move towards each other. So we need to eliminate these demagnetizing fields. So well, before I come back to that, let me just show you, I want to try to discuss the mechanism, which is extremely interesting. So if we pass, as I mentioned, current into platinum, or a material with strong spin-orbit coupling, then we generate, through what's called the spin Hall effect, a spin polarized current. So on each surface of the platinum layer, we have a chiral current that is formed. So on the top surface of the platinum, we pass current in this direction, which is charge current, and we generate a spin current in exactly the perpendicular direction, with a spin that is in the perpendicular direction, but on the bottom surface, that spin current will flow in exactly the opposite direction. So we have a chiral spin current flowing around the surface of this platinum wire, if you like. So this is, again, a chiral phenomenon where we're breaking symmetry to generate a spin current in one direction, polarized in one direction on one surface. And the question has been for the last 2 or 3 years, how big is the spin current that we generate? And that's an unanswered question today, but a very, very interesting one. But at least in platinum, it seems that for every electron that is traveling in this direction, we get about 1/10 of a spin polarized electron perpendicular to that charge current. There's been some very interesting recent work where a group at Cornell and a group at UCLA have claimed that using topological insulators, they can see for every charge electron flowing this way, they get 100 spin polarized electrons flowing perpendicular to the current, which would certainly be an amazing phenomenon. Well, the concept now is we generate then in this non-magnetic layer, we generate a spin current that then diffuses into the magnetic film and causes magnetization to rotate, because that spin current again carries spin angular momentum. And now, just as an aside, let me point out then that a very important ingredient in understanding this phenomenon is something called the Dzyaloshiinski-Moriya interaction, which was again known in the 1960s and 70s, that under special circumstances in materials with strong spin-orbit coupling, the magnetizations no longer want to point parallel or antiparallel, as in conventional ferromagnetic or anti-ferromagnetic materials. They want to be pointed perpendicular to each other in a vector direction. So they want to be perpendicular in a chiral orientation. And this is a very, very interesting phenomenon. And this is extremely important to understanding how the domain walls move in these layers. So let me just show you a cartoon. Here we're looking at the top of one of these racetracks, where here the magnetization is pointing out of this plane, and here it's pointing into the plane. Now what happens then is that the magnetic moment in the domain wall is so-called of a nail type. The magnetization rotates from up to down in a plane parallel to the length of the wire. And the magnetization is chiral, we believe, due to this Dzyaloshiinski-Moriya interaction. So in this case, the magnetization always points to the left. It never points to the right, which would otherwise be an equal energy. But we've broken the symmetry using the DMI interaction from the surface with this platinum layer. And so if we reverse the next domain wall, which goes from magnetization pointing down to up, here the magnetization in this wall points to the right. And it turns out this is what we've discovered, that this magnetization will always point to the left for the up-down wall, always to the right for the up domain wall, because of a Dzyaloshiinski-Moriya interaction. And it looks like that interaction looks like the moments in the domain wall see a large longitudinal field, which is either pointing for this domain wall to the left or for this domain wall to the right. It's a chiral magnetic field derived from this chiral exchange interaction. So now what happens? If we now flow current through this device, then we develop a spin polarized current, a pure spin current, perpendicular to the wire, as shown here. Now what happens? This current of spin polarized electrons causes the magnetization that was parallel to this direction to rotate towards this spin direction. So it's very different from a magnetic field. Because this is delivering spin angular momentum, it looks like a torque, and it causes the magnetization then to want to rotate towards the spin current for this configuration of the domain wall as for this configuration of the domain wall. And what does that mean? Now, because of this field that the domain wall sees derived from this Dzyaloshiinski-Moriya interaction, then this field gives rise to a torque on this magnetization, wanting it to rotate in a particular direction. And because of the chiral nature of this Dzyaloshiinski-Moriya field, this means that in this case, these blue moments will rotate in this direction, and these red moments will rotate so they move in this direction. And these domain walls all move in the same direction only because of the fact that the domain walls have this chiral structure imposed on them through this Dzyaloshiinski-Moriya interaction generated at an interface with a heavy metal underneath them. And then this field torque moves the domain walls along the current flow direction. This is what happens. And now we can then show the domain walls, A, move much faster. We've demonstrated velocities of several hundred meters per second, as I mentioned, in these upper racetracks. But now to overcome these dipolar fields, we now build a racetrack which has two racetracks. The lower racetrack has its magnetization in every single part of the racetrack in these directions, and it's coupled through a very thin layer of ruthenium that couples the moments in the upper racetrack exactly opposite, anti-ferromagnetically, to the moments in the lower racetrack. So this net racetrack has no net magnetization, and what we've discovered is that the domain walls move 5 times faster than in the single racetrack here. And this is because of a completely new chiral torque that we've discovered. We have a paper which I hope Nature Nanotechnology will shortly accept, in which you can see here in this image the domain walls now in this synthetic anti-ferromagnetic racetrack. You can see many of them moving backwards and forwards, but the racetrack now has no net magnetization. We've made the magnetization disappear. And it turns out the domain walls move 5 times more efficiently, up to velocities of about 1,000 meters per second for the same current density as in the very first racetracks I showed you, where they were moving at 50 meters per second. So in the space of 3 years, we've increased the velocity by 20 times using these novel structures. So that's the end of my talk. I basically discussed Racetrack Memory, which has a storage capacity of up to 100 times, or even now we think 250 times, the storage capacity of any conventional solid-state memory. And so I think we're now on a path to developing prototypes of this vertical racetrack. And if we succeed, we believe, or I believe, this racetrack memory could certainly displace flash memory and provide a much faster, more reliable, more energy efficient storage device, and could potentially replace hard disk drives to make and would use much less energy. And the point is that racetrack memory, I think, is a future, the breed of all future devices, which means we have to move from today's two-dimensional devices. Magnetic disk drives is a two-dimensional layer of magnetic material. Silicon is a two-dimensional layer of transistors. We need to move to more innately three-dimensional devices because we've reached the limits of scaling in the two-dimensional geometries. And racetrack memory then is, I believe, an innately three-dimensional device that takes advantage of new physics that enables this to be possible. And I was going to talk, but no time, to talk about cognitive devices, again, entirely three-dimensional devices that we could use to mimic how we think in the brain, to build devices that could be a million times more energy efficient than charge-based computing devices. But I think I'll stop here, and I want to thank you very much for your attention.